Okay, welcome everyone to today's TCS Plus talk. Thank you very much for being here. We have an unprecedented turnout for a number of reasons. I'll mention that 3 weeks from now, we're going to have our next speaker, which is Venkat Guruswamy. Notice it's going to be 3 weeks rather than 2 weeks. We're going a little bit off schedule to accommodate for the Fox deadline. We don't want to talk like the day before the Fox deadline, so we're being, we thought about that. But yeah, like I said, today we have an unprecedented turnout for a couple reasons. Well, first of all, as you all know, many people are, staying home and joining as individuals today, which I think is good, a good practice. But on top of that, I think I just want to brag a bit and say that TCS Plus was prepared for this 7 years ago. So thank you for, participating in this experiment. Second of all, I want to say that this is, I think there's an unprecedented turnout just because so many people are really interested in this result. I've seen a lot of people who I don't think would normally join TCS Plus joining today. So I want to thank you all and welcome to any first-time joiners. So without further ado, let me tell you about today's talk. Today's talk is going to be given by Thomas Steinke, who we're very excited to have. Thomas is a researcher at IBM Almaden. Before being a researcher there, he did his postdoc there as well. And before that, he did his PhD at Harvard University. Thomas is interested, of course, as you can see today, in learning and generalization, but he's also very well known for a lot of his work on differential privacy and also some work in pseudo-randomness. So without further ado, I'm going to pass it off to Thomas. Yeah, Thomas, I'm going to spotlight you. And can you share your screen, please?
Okay. PowerPoint.
There we go.
Okay.
Yeah, without further ado, thank you, Thomas.
Okay, great. Thank you very much. Thanks for the kind introduction and for inviting me to speak. Okay, so let's just start with an overview of this talk. So I'll start with a very slow introduction to the basic background on the topic of generalization, and then looking at the connection to information theory via mutual information before introducing the perspective that we have of conditional mutual information. And then I'll talk about the actual results, which is firstly that CMI, the bounds on the conditional mutual information, imply generalization. And then, of course, that we can obtain bounds on the conditional mutual information from various known techniques. And then we'll conclude. So just, feel free to interrupt me with any questions. I'll try to pause every now and then so you have time to find where the unmute button is. Okay, so the setting we're working in is just the standard statistical machine learning system. Setting there is a unknown population. You receive a bunch of samples from that, and you stick that into your algorithm, and you get out some model or hypothesis. And the goal here is to learn about the world from the data, but the problem is that data is only a finite sample, so it may not be fully representative. And the thing that we're worried about is the overfitting, which is failing to generalize, which basically means we're fitting chance patterns in the data. So you've probably all seen a picture like this, sort of illustrating what overfitting looks like. It's where you're fitting all the randomness in your data rather than the actual underlying pattern. And the scientific question here is basically, why do certain algorithms generalize? And that feeds into the engineering question, which is how can we actually design algorithms to generalize better? And I think it's fair to say these are extremely well-studied problems. There's many different methods that have been proposed to prove or analyze generalization. And I will not talk about more than 2% of these. And there's a lot there. But still, there's a lot of things that are unknown about generalization. And sort of the motivation of this work is to see if we can take some of these methods and unify them into something more coherent, because I think in some respects the theory is rather disjointed. Okay, so let me give you a precise model for what we're studying, just introduce some of the notation and terminology. So we have some probability distribution D, and we have a sample, which we'll denote by Z or Z if you come from New Zealand, which is consisting of n IID samples. And then there's a loss function, which is measuring the quality or veracity of whatever model or hypothesis you produce. So one example to keep in mind is just 0, 1 loss. So each of your points Z is going to be a feature vector X and a label Y, and your hypothesis or model corresponds to a function, and you're just going to give 1 if the function is accurate on that point, and 0 if it's 1 if it's inaccurate, and 0 if it is accurate. And then the two key quantities that we're looking at is the true loss, which is the expectation of that loss for a single random sample from the distribution. And the other thing we're going to be comparing to is the empirical loss, which is the loss averaged over the sample that you have. Now, it's worth noting these are linear loss functions as I've defined them, because they take in a single point from the distribution, a single sample. But what we talk about here could extend to nonlinear loss functions as well, and I'll mention those briefly later. Now, the goal is just to find some minimizer of the true loss. But the problem, of course, is that we don't have access to that distribution, so we have to work with some proxy, such as the empirical loss. And one natural learning strategy is just to minimize the empirical loss. It's called empirical risk minimization. And the generalization question, which may be more formal, is just how can we ensure that the loss at the hypothesis that we end up selecting, I'll call that W star, is approximately the same on the empirical distribution, so on the sample Z, and the true distribution D. And let me know if you have any questions about the basic setup of everything. Okay, so let's just talk about some of the basic techniques for how people study generalization. So the most classical theory, which dates from the early 70s, is uniform, at least the early 70s, is uniform convergence. And the idea is this: if we can show that for all hypotheses W, the empirical loss is close to the true loss, then we're safe, because now if we are minimizing the empirical loss, we're also approximately minimizing the true losses. There's a stronger condition than what one might need. And one of the key ideas in uniform convergence is what is dubbed Occam's razor, which is that simple models generalize, and one measure of simplicity or complexity is the VC dimension. And you can show that if the hypothesis space has bounded VC dimension, then with high probability, the loss on each hypothesis in that space is close between the empirical and the true value. And this is, of course, related to regularization. But the thing I want to point out is that this is only a property of the output space, the hypothesis class W. And it is not a property of the algorithm for picking the hypothesis. And as we move on in this talk, we're going to be thinking more about what that algorithm is, and we're going to think of generalization as a property of the algorithm rather than just a property of the output. So the other method for proving generalization that I want to mention is distributional stability, and the most famous form of distributional stability is differential privacy. Now, as the name suggests, differential privacy is a standard for privacy-preserving data analysis that basically ensures that if you run some algorithm, then the private details contained in the training data don't leak through the output. Now, that's not what we're concerned about here. We're concerned about generalization, but it turns out the differential privacy does imply generalization. And this is particularly useful in the setting of adaptive data analysis. And this was a connection that was studied starting in 2014. So let me just, in a brief cartoon, explain what adaptive data analysis is. So the way scientists are taught to do data analysis starting from high school is basically a sequential process. You form a hypothesis, you collect your data, and then you test that hypothesis. But then in practice, people are not following that, because if the hypothesis turns out not to be right, you go back, you revise it, And instead of collecting fresh data, you just reuse the data you have, and you iterate until you find a hypothesis or conclusion that works for you. And unfortunately, this process really is not good for generalization. And the key thing is this iteration and continual adaptation. And it turns out that differential privacy provides very good guarantees in this setting of adaptive data reuse. Now, for completeness, I'm going to put the definition of differential privacy up on the screen. So basically, it's a condition that says if you change one element in your data set, so you go from Z to Z prime, then the probability of any event can change by at most a multiplicative e to the epsilon plus an additive delta term. So basically, it says that the distribution is stable when you make small changes to the input. Okay, so the point here is that there are many different generalization methods. I've briefly mentioned uniform convergence, which has within it a wide variety of techniques. Also briefly mentioned different distributional stability. Again, there's also a wide variety of things that fall under that hat. And there's other things like compression schemes or uniform stability or loss stability, as I like to call it, and plenty of other things. But I would point that, despite all of these methods, there's plenty that is not understood. So essentially, the goal of this work is to try and unify some of these different approaches, particularly the what we started out with. So this was a summer project. We decided, can we come up with a definition that is sort of a least common generalization of both VC dimension and differential privacy. And the way we do that is by providing an information-theoretic perspective on generalization. Okay, so now let's talk about the connection between information theory and generalization. Before I do that, are there any questions? Okay, so there have been many different connections between information theory and generalization. So one unrelated line of work is things like the information bottleneck. But what I'm looking at here is looking at the mutual information. And this is something that's been studied in previous work. So the idea is to consider the mutual information between the input of my algorithm, which is the NIID samples, and the output, which is the trained model. And intuitively, what this is measuring is how much does the output of the algorithm reveal about its input, or another way to put it is, given the output, how well could I reconstruct the input? Now, it turns out that having low mutual information, this unconditional mutual information, does imply generalization. And kind of the sanity check here is if the mutual information is 0, then the output of the algorithm is independent from its input. So you're basically, in this case, we have a fixed hypothesis and we know how to analyze that. That's just some standard concentration inequality. And it turns out if it's close to 0, then you also get a reasonable amount of generalization. So it's not too surprising that this implies generalization. Okay, so what can we actually do with this unconditional mutual information? So differential privacy does imply bounds on mutual information, but only if this delta parameter is 0. If it's non-zero, then it doesn't work. So we are capturing something here, but it doesn't quite work. Another one is I have a small hypothesis class. I'm also going to have low mutual information. And the reason is simply that the mutual information is upper bounded by the entropy, and the entropy is at most the log of the support size, which is the hypothesis class. So that's giving you another type of generalization being wrapped up in here. So the next question, of course, is what about something like VC dimension? And there was a very beautiful result by Raif Basili, Shai Moran, Ido Nahum, Jonathan Schleifer, and Amir Yehudayov from 2018, where they showed that unfortunately there exists a hypothesis class with VC dimension 1, so extremely simple hypothesis class, but infinite, such that any consistent learner is going to have unbounded mutual information for some worst case distribution. And these hypotheses are just threshold functions, which are one-dimensional linear classifiers. Okay, so kind of the problem here, both on both the connection to VC dimension and looking at distributional stability, is that if you have a continuous distribution, then a single sample from that distribution has infinite entropy. And that means that the mutual information easily gets out of control, goes to infinity, even when you're in a situation where generalization is working perfectly well. So it's kind of not quite capturing what we want. So that's the starting point for the work that we did. So let's look at how we address this. So we're going to fix this problem. So the intuition that I have is that we're going to fix the problem of just looking at mutual information by normalizing the information content of each sample to just one bit. And the way we do this is essentially we say, instead of considering the full distribution, which could have infinite entropy, we're going to first narrow it down to two possibilities. And now we're just going to look at the entropy relative to those two possibilities, which of course is one bit. And an alternative intuition is to say, well, instead of asking how well could I reconstruct the input from the output, so just unprompted come up with a reconstruction of the input, I ask, if you give me a set of candidates, a lineup, how well can I recognize which of these are the input and which are not? So there's a difference between trying to come up with a sketch of some criminal and having to pick out that criminal from some lineup. The second task is a lot easier. I mean, of course, in this case, the criminals are just our input data. And the idea is that there's a much lower information content if I give you a set of candidates and ask you to choose. Okay, so let me start showing you how we formulate this intuition into a precise definition. So the first step is, instead of drawing n samples, I'm going to draw two n samples. And I'm going to call this the super sample. And now what I'm going to do is I'm going to take these two n samples and I'm going to evenly partition them into the actual input, which I'm going to denote z sub s. And and the other half is going to be the ghost samples, z sub complement of s. And now this s here is going to be what's specifying the partition. Now it's going to be consisting of n uniform bits independent of everything else. And the idea is that for each point in the sample, there's two candidates within the super sample. And then there's a bit that tells you which of those is chosen. Now we run the algorithm on the chosen sample, z sub s, and obtain an output. And the quantity that we measure is the mutual information between the output and that s, which is telling us which bits are included in the sample versus the ghost sample. And we're now conditioning on the super sample. So we're taking that those two n samples as given. So the idea here again is I'm giving you a set of two n samples. I'm showing that to you. There's no entropy there because of conditioning on that. And now I'm just asking you to tell me which of those are in the sample and which are not, which is just n bits, telling me for each of the sample there are two candidates, which of them is it? So I'm just asking you to distinguish between the input samples and the ghost samples.
Just to distinguish this from before,
Yeah.
Before you were considering like the mutual information between A of Z sub S and Z sub S?
Yeah.
Okay, got it.
Sorry, quick question, Thomas.
Yeah.
The partition is also known?
No, the partition is unknown, and I'm like seeing how well could I reconstruct that partition from the output.
But like which one is in the two choices? So that's all that's not known.
Oh yeah. So I know which one is which two candidates there are for each given input.
And sorry, one more question. The two samples, are they exactly the same size or just in expectation?
They're exactly the same size.
Then how come the bits of S are independent?
So the way I'm doing it is for each of the n inputs, there's two candidates. And I just have one bit for each input telling me which of the two candidates it is.
Sorry, the bits are not saying whether each sample goes into like S or S bar. Or...
Yeah, so it's not that I'm like...
There's only n bits, not 2n bits.
Yeah, so it's not that I'm looking at all like 2n choose n possible partitions. I've like looked at a subspace of partitions where there's only 2 to the n partitions. And essentially like for each candidate, it's only going to go to like input I. It's not going to go to input, 3i. There's only one place it could go. So that reduces the entropy.
Okay. I got it. Yeah.
So yeah, here's the formal definition, and I'll just slowly walk through this. It's exactly what I walked through on the previous page, but it's important to go through it slowly. So we have some algorithm which is randomized or deterministic, and then we have some distribution D. Now I'm drawing 2n independent samples from that distribution, and I have some S, which is n random bits, and I'm assuming everything is independent. So now the Z sub S is going to be the n elements of the supersample Z that are indexed by S. And just to sort of be precise in terms of my notation, the ith bit of the sample Z sub S is going to be either Z sub 2i or Z sub 2i minus 1. And which of those two it is determined by S sub I. And now the conditional mutual information is going to be precisely the conditional mutual information between the output, those n bits S, conditioned on that fixed, I mean, it's random, but we should think of it as fixed supersample Z. Okay, yeah, so just unpacking that again, we have a supersample. It is containing n samples and n ghost samples. We don't yet know which is which. We have a selector that chooses. And the key thing is that for each sample, there's only 2 candidates. We just have 1 bit telling us which is which. And then the actual sample still has the marginal distribution of being n IIT samples from the distribution. And we're going to measure how well we can distinguish the samples from the ghost samples using mutual information. Okay, so let's try to interpret this, what this quantity means. So just putting the notation up there again. And the definition. So I don't know how familiar people are with mutual information, but let's sort of try to unpack what this quantity is measuring. So the first thing to note is that mutual information is always non-negative. Now we can express it in terms of the entropy. So we can express it as the entropy of the output conditioned on the supersample Z minus the entropy of the output conditioned on both the supersample Z and the selector S. So you can think of the second term as being the randomness introduced by the algorithm itself. And the first term is the randomness of the algorithm and of the sample. Now, since entropy is non-negative, this is at most the entropy of the output conditioned on Z, And again, like before, it's at most the logarithm of the support size. So this particular expression is useful for proving upper bounds on the CMI, and I'll show you how to do that a bit later. Now, CMI is also, mutual information is a symmetric function. So we can also express this as the entropy of the selector S minus the entropy of the selector S conditioned on the output. And now the entropy of the selector is always n bits, since those uniform and independent, minus the entropy here. So this expression is useful because it tells us that the CMI is at most n bits, so that gives you an upper bound. And it also gives you some idea that you could interpret CMI as being how well can I predict S given the output of A. It's a little weird that this is now negative, but that's kind of one way I like to interpret it, is that how well could I predict those bits S given the output. So another way to view mutual information is as a KL divergence. So another equivalent definition of mutual information is that it's the KL divergence between the joint distribution of the output and the other thing S versus a productized version of that. So it's a KL divergence of the joint distribution from this product distribution, where I'm just thinking of S prime as just being an independent copy of S, and conditioning is just averaging over Z. Now this expression is useful for deriving generalization bounds from CMI, because what I'm effectively saying is that this joint distribution I'm trying to analyze is close to something that's a product distribution, is therefore easier to analyze. Okay, any questions at this point?
Question, Thomas. So that last expression, it's the expectation over Z, but inside I condition on Z, right?
Yeah.
Z is fixed for the purpose of computing.
Right.
KL divergence.
Yeah. So it's also equivalent to looking at the KL divergence of the triple output S Z.
And Z, right.
Yeah. Yeah. Unfortunately, the notation for this stuff, it's really deficient. I don't think I know what the right notation is for expressing a lot of these concepts.
This is Prakash Narayan. There's one way of getting around it. Often in information theory, at this point, there's a conditioning on Z that is used. Then you spare the divergence of all of this and then put a conditioning here. And the understanding is that the expectation eventually is with respect to Z. And it also addresses the previous question that when you look at these two divergences, they are of these joint distributions, each of them conditioned on Z.
Yes. Yeah. There's a lot of different expressions we could put in here.
Yeah. Is it possible that the conditional, the entropy condition on Z and S be negative if the output of the algorithm is in some continuous space, like a real line?
Yeah, so things could get messy if you are in continuous space. So some of these definitions do not make sense if things are continuous. But if you define everything in terms of KL divergence, generally things work out fine. You know, KL divergence is perfectly well defined and well behaved for continuous distributions, as long as you avoid any issues of non-measurability and non-absolute continuity. Yeah, but you're right that these expressions in terms of entropy do not make sense if you have a continuous distribution. Okay, so let me just go over the properties of this this thing. So even if you didn't really understand the inner workings of the definition, really the key thing you need to know is that it's a property of an algorithm and a distribution, although we could also define it without a distribution. Let's look at the worst case z, but let's not talk about that. But it doesn't depend on the loss function. And it's just a number that's somewhere between 0 and n bits. Now, it retains the nice properties of the unconditional mutual information approach in the previous work. The first is that if you have low conditional mutual information, that's going to imply generalization. And just sort of to give you some more intuition about what the parameters mean, if the CMI is sort of sublinear in n, that's going to roughly correspond to getting good generalization. Now, I'll be a bit more precise about the quantitative relationship later, but that's just sort of the rough intuition. Now, as before, we are able to show that something like pure differential privacy implies bounded CMI, and it also has nice properties, which are dubbed post-processing and non-adaptive composition. These just mean if I run 2 algorithms on the same data set independently, then the CMI of the combined output is just the sum of the 2 CMIs. And if I also perform some post-processing, which is to say I take the output, apply some function to it, and then give an output, that is also not going to increase the CMI. So this is just sort of nice robustness properties. Now, the key things that we gain over the unconditional approach is, firstly, it's always finite. So it never goes off, it's never unbounded. Now, this is in itself not really that useful, but it is useful. It does indicate something is being done better. And one particular thing we can show is if I have an algorithm that just outputs a random subset of its inputs, right? So maybe I just have an algorithm that outputs the first of its inputs, just doesn't do anything interesting. This is going to have a CMI of just 1 bit. I'm revealing one input that's going to tell me one of these things. It's not going to tell me anything about anything else. And that kind of corresponds to what we would expect for generalization. We don't expect that revealing just one of your inputs is going to really significantly impact on generalization. Whereas with the unconditional mutual information approach, that is not the case. Revealing one input could have infinite entropy. Okay, so we also show that it can be bounded via VC dimension, which was something that we couldn't do with unconditional mutual information. And we can also bound it via compression schemes, which is another way, a related way of proving generalization. And we can also prove it from approximate differential privacy, which is when you have non-zero delta. So we're able to show that this can be bounded from weaker versions of distributional stability. So the idea is that we're able to incorporate more things under this hat. And maybe the thing to emphasize is that if I take a bound on VC dimension, convert that into a bound on conditional mutual information, and then get a generalization result out of it, this is going to give me a result that's similar, not exactly the same, as going directly from VC to generalization. I'm just going to lose sort of a log factor, basically. So that's sort of telling us that this connection is not is relatively tight. I'm not losing too much by going through this. Okay, so let me now talk to you about what does low CMI imply. So the first result is just saying if we have a bounded linear loss function. So here we have an algorithm, a distribution, and we obtain n samples. And we're going to consider a loss function that is linear in the sense that it only depends on a single input bit. And then it's bounded between 0 and 1. So the first result just says that the empirical loss is an expectation close to the true loss, and we get this, this bound here. And that's exactly what we'd have gotten with unconditional mutual information. So we haven't lost anything by switching to the conditional case, to conditional mutual information in this case. So just a reminder, the empirical loss is the average over the data set, whereas the true loss is the average over the unknown distribution. Now we can obtain a stronger result by looking at the expected squared difference between these two. And that gives us about here, it's weaker only in these two little constants here. So we're able to get this result. And another thing that we're able to get is this multiplicative version of the bound. And this is useful if you're in the setting where you're either realizable, so this loss here, the empirical loss is 0, or this is also the overfitted case, or sometimes referred to as the interpolating case. So if you have that, then you get a stronger generalization result. In fact, you get essentially a quadratically better bound on the expected true loss. So instead of basically this quantity conditional mutual information of n comes outside the square root. So we're getting a better result in the realizable / overfitted setting.
Thomas, which of these hold under mutual information versus CMI?
The first one holds under mutual information. I suspect the later ones do too, but I don't think that's been proved.
Okay, thanks.
So I mean, the key thing with the first result is we're not losing anything, not even in constants relative to mutual information.
Maybe one note is that at least the second statement was, some version of it is definitely proved for mutual information.
Yeah, I mean, I imagine these things are easily proved from mutual information. I just haven't seen them.
Like anyway, whatever. They're in the original papers that prove the other one too.
Oh yeah, I think there was something in the Rousseau-Zoe paper similar to this.
That's right.
Yeah. Okay. Yeah, I mean, the point is here we're getting, these are sort of very standard formulations of generalization results for a bounded loss function. This is exactly what we were getting for the unconditional mutual information case. So by conditioning, we haven't lost anything in terms of its implication for generalization. Okay, so the obvious next question would be, well, what if we have an unbounded loss function? And we can obtain results in this scenario too. So now we have a loss function that's unbounded, with values all over the reals. And we still get a generalization result, but now you're looking at, but you still have to have some kind of scale in here. So this scale here is basically this expected square of the loss, but you're maximizing over all hypotheses. Now, it's worth noting that this z prime is just a single sample. And we lose a constant, but that's not important. So just to sort of give you some idea of what this might be useful for, so one application is the hinge loss. So this is what you would use to train a support vector machine. Now this is unbounded, but we're able to show that we get a bound on the loss, which scales with sort of the variance of your data. So if your data is unbounded but still has finite variance, you're going to get some kind of generalization done out of this. Similarly with squared loss, so mean squared error, which is sort of the standard for linear regression, we can then obtain a bound for that using the fourth moment or something like that. So just wanted to point out that this also works for unbounded losses. And we are also able to extend this to nonlinear losses. We have a loss function that takes in 2 points or more points. The general statement is buried in our paper. I won't put it here. It's not really suitable for slides, but I'll just give you one example application. So let's look at the area under the curve, the area under the ROC curve, which is a very commonly used nonlinear statistic. And it's basically, if I have some score function, now you can take a score function, turn it into a binary classifier by thresholding. We want to look at the probability that a random positive example has a score larger than a random negative example. So this is probability here for positive example has greater score than negative example, and I'm conditioning on the z plus being a positive example, z minus being a negative example. So there's some arbitrary set of positive and negative examples. Then we can get a generalization result for that. So let me just walk through the statement. So we have a randomized algorithm, outputs a score function of a distribution, and there's some subset z plus of the support, which is the positive examples. And then we have this p, which is the probability that a random example is positive. We take n samples, the probability that the empirical AUC, the probability that the empirical AUC and the true AUC are with an epsilon is at least 1 minus order CMI over n, epsilon squared, and then there's this p1 minus p. Now this is kind of the right set of parameters, so you have to have this 1 over p minus 1 minus p, because if p is too close to 0, you're just not going to get enough positive examples to do any estimation. Yeah, so this is just an example showing that from CMI we're able to get generalization bounds for nonlinear loss functions, which is, I think, very neat because a lot of approaches don't really naturally yield that.
Question, Thomas. Yeah. Sorry, say again, why is the 1 over p factor necessary?
Well, I mean, imagine if I have a distribution that just doesn't have any support on positive examples.
Yeah.
Like, there's just no way I'm going to be able to estimate the AUC.
Oh, because it's a conditional probability. I see.
Right. Like, I'll just never see any positive examples and never be able to estimate it.
That makes sense. Okay, now I get it.
Yeah. So I mean, basically, this is the right parameters. Like, of the parameters considered, this is the right dependence. I am hiding a nasty constant in here, though. The proof was a bit messy.
Hey, Thomas, can I ask another question?
Yeah.
Which of these last 2 slides also work with just regular mutual information? Do they both work, or yeah, like?
I don't know. I mean, I haven't thought about that. They probably do. I mean, my intuition is that regular mutual information is stronger than conditional mutual information. It's not precisely true, but I think anything that works with CMI should work with just MI. Okay, so I've given you sort of a sequence of examples, and looked at the expectation, the expected squared error, multiplicative form, unbounded losses, nonlinear losses. And this is just a sort of a sequence of examples to illustrate that CMI does give a versatile array of generalization bounds. And one other thing I want to emphasize is that since the CMI does not depend on the loss functions, you can get these bounds for any loss. So if I could substitute in some slightly different surrogate loss and get a different bound from these. So I hope that these results have sort of illustrated that it's very versatile, and it is really, I think, actually capturing what generalization should be, or at least it's a sufficient condition to say that an algorithm generalizes. One other note is most of the results I stated are expectation bounds. So I'm just saying the expected loss or expected squared loss is small, but we can get probability bounds via, we can easily get sort of bounds in terms of probability from these or from other statements that are in the paper via something like Markov or Chebyshev's inequality. So, for example, if I have a 0-1 bounded loss, and a corollary of the result I showed you is that probability that your error, your generalization error, is greater than epsilon is sort of CMI, the conditional mutual information divided by epsilon squared n, which is roughly the right dependence. But I will note that this isn't really a high probability bound. So we're used to having bounds where you have an exponential term on the right-hand side over here. We'd expect something more like e to the minus epsilon squared n instead of just a 1 over epsilon squared n. Now, this is an inherent limitation of the approach because we're using mutual information, which is an expectation. So if there's a small probability that you're getting sort of a very bad outcome that's massively overfitting, it's only going to boost the CMI by like a probability times n. So it's just not that sensitive to these bad events. So, one direction, of course, for future work is to try and incorporate some kind of variant of mutual information that's that's better at picking up the low probability events and giving us high probability generalization bounds. Although I note that high probability bounds often you just get them for free, or there's an easy way to amplify. So I'm not too worried about that. I don't think that's a critical part of the story. Okay, so I just want to give you a very brief idea of what goes into the proof of these generalization results. And there's essentially two ingredients. So the first ingredient is just saying that if the CMI is low, you're going to get two similar distributions. So the first distribution is the joint distribution of the output, A of Z sub S, the selector S and Z. And the second distribution is the output, A of Z sub S, and an independent copy of S. So it's just n random, uniformly random bits, and S. And in fact, the CMI is precisely the KL divergence between these two distributions. So that's the first ingredient in proving these results. The other ingredient is just concentration of measure, which of course is a tool we all know and love. And we know that for reasonable loss functions, such as bounded loss functions, with high probability, the empirical loss, or the loss of a hypothesis on Z sub S, is close to its true loss. And the same is also true of the ghost samples. So the loss on the ghost samples is close to the true loss. And the way we combine this is we look at some function of the following form. So we look at the loss on the sample, the loss of our hypothesis W on the sample Z sub S, and we subtract the loss on the ghost samples. Now the quantity of interest, the thing that we're trying to bound, is effectively F of output, S, and Z. If you substitute that in here, you're going to get the empirical loss here and the loss on the ghost samples. But the loss on the ghost samples, since the ghost samples are independent of the output, is just a proxy for the true loss. So effectively, this F here is going to give me the empirical loss minus the true loss. Now, concentration tells us that if I were to replace S with an independent S prime, then with high probability, this function is going to be close to 0. And this is not exactly a corollary of the type of concentration results we want, but it's the same idea, same techniques. And basically, the idea is that CMI allows us to relate these two. So you've got one thing that's close to 0 with high probability. The other thing is what we're interested in. And we know that they're close in KL divergence. And we also have this data processing inequality. So applying the F isn't going to change that. And just combining these ingredients gives us these generalization results. So there's no real magic here. That's all the detail I want to give. Let me know if there's any questions. Okay, so as we move on, let's talk about actually obtaining bounds in the CMI. So the first thing I'll talk about is how do you obtain it from distributional stability. So just flashing up the definition of distributional stability. An algorithm is distributionally stable if changing one of its inputs doesn't change the output distribution too much. I want to convert this into a bound on CMI, and the ingredient is simply the chain rule for mutual information. So CMI is this mutual information, By the chain rule, I can write this as a sum of the mutual information between the output and a single bit of SI, a single bit of S, conditioned on Z, and also S1 through Si minus 1. Now it turns out that that since the S's are just independent bits, we could just condition on the entirety of S1 through Si minus 1 plus Si plus 1 up to Sn. And now this is a very easy quantity to bound. You can just write it out as a KL divergence, where these distributions are going to be conditioning on the value of that Si. And distributional stability is telling us that these things are close, and that's all we need to complete the proof. We just plug in distributional stability with the chain rule, and this quantity here is known as a Jensen-Shannon divergence. Okay, so the key thing I want to get from this slide is it's just the chain rule for mutual information allows us to convert distributional stability to bounds on CMI. And one example result is if you have delta total variation stability, that's going to give you a CMI of n times delta. This is not something that is true for unconditional mutual information. Any question? How are we doing on time? I don't have a...
Maybe like another 10 minutes until like 11, but
okay.
You know, try to wrap it up.
Yeah, that's
we got this time.
Fine. Thomas, I have a question.
Yeah.
So, condition on Z, the input here is a product from a product distribution, right? That's what's going on in this proof. And so like there are a bunch of statements scattered in the literature of the form, you know, if the input is from a product distribution and your algorithm satisfies criteria N, X, Y, or Z, then such and such a measure of information is bounded, right? You can just use those like almost verbatim, right?
Yeah, exactly. And that's exactly what we do. The only thing that's new is for the TV stability, which doesn't, as far as I know, previously exist in the literature. And you just have to show this Jensen-Shannon divergence is bounded by total variation distance, which is known, that's in the literature.
Okay, thanks.
Okay, so the other result I want to tell you is bounding the CMI from VC dimension. Now, I assume most people know what VC dimension is, but it's just a classical measure of the complexity of a class of Boolean functions. It's always got a trivial upper bound of log of the size of that, and something like a linear threshold function has VC dimension equal to the dimension of the space in which you're taking your linear functions over. And of course, VC dimension implies uniform convergence, and hence as a sufficient condition for generalization. But one thing I want to note here is that there is a type mismatch. So the conditional information is a property of an algorithm, whereas the VC dimension is a property of the hypothesis class. So we show that for any hypothesis class, there exists an algorithm that is a ERM and has low CMI. But it's not true that all ERMs have low CMI. So here's the precise statement. So we have some class W of functions with a VC dimension D. Now, just notation, I'm going to let Z be space of examples, which is an X and a label and 0, 1. And I'm just going to look at the 0, 1 loss. So 0 if the function is accurate on that point, and 1 if the function is inaccurate. So there exists an algorithm, which is in fact deterministic, that takes n examples, outputs a hypothesis, and it has CMI at most d log n plus constant for every distribution. And it's an ERM in the sense that the loss of its output is always the minimum possible loss of any function in that class. Okay, so the proof is pretty simple. We have 2 steps. So the first is we show that any algorithm with a certain consistency property has low CMI. And then we show that there always exists an ERM with that that consistency property. Now, the consistency property is something that's fairly natural. Let's say, suppose I run my algorithm A on a set of features X and corresponding labels Y and obtain a hypothesis H. Now, if I were to then relabel all of those examples to be consistent with H, I should still get H back. And I think that's fairly natural because, if I picked H with the original labels and then I just change the labels to be 100% consistent with H, then surely I should output H again. And this should hold even if I add more examples. So now I add 2x to get x prime, where those new examples are also consistent with H. So basically, making the labels consistent shouldn't really change the output hypothesis. Like, really would be, so in my opinion, this is sort of a very natural condition. Of course, you can come up with pathological examples that don't have it, but I think most non-pathological algorithms should have this consistency property. And the only thing you have to be careful about is when you have multiple ERMs, so multiple hypotheses with minimal loss, you have to find a way of breaking those ties in a consistent manner. And the way we did it, just use a well ordering. So this works for any hypothesis class as long as you believe in the axiom of choice. So there's nothing exciting in the second step of this proof. So on the next slide, I'll just tell you what is the first step of that proof, which is to say, how do we show that any algorithm with this consistency property has low CMI? So we're trying to prove that any algorithm with consistency property has low CMI. And this is the consistency property. So let's just write out the CMI. And we just use the fact that it's upper bounded by the entropy of the output conditioned on supersample Z. And that entropy is at most the support size. So it's at most the log of the set of outputs that A has over all possible selectors S. Now, obviously, this set could be as large as 2 to the n in general, but we'll show that it's not that large. So just a bit of a notation. I'm going to sort of break up my Z into the features X and the labels Y. And now the key step is that I use my consistency property. So essentially, this set that I'm interested in, the set of all possible outputs for a fixed supersample Z, is just going to be generated by looking at all possible labelings of the examples in my supersample. And this is fairly easy to show as a corollary of the consistency property. And the key thing now is that instead of counting all of these outputs, I just need to count all the possible labelings H of X of my 2n examples in the supersample. And that's something that we can bound using the Sauer's lemma. So we get a bound which is n to the order VC dimension. Now we just substitute that bound on the cardinality into this, and we get exactly the result that we wanted. So fairly straightforward. Okay, just putting the statement up again. So one thing I do want to mention is that we conjecture that we could get rid of this log factor and shave that off. Any questions at this stage?
I had another question. Yeah. Is there some similar property that you could state for randomized algorithms here? Like you had the consistency thing, but yeah, what about randomized?
We didn't really think about that. Like we just wanted some property that would make the proof work. I think very naturally you could do something for randomized algorithms. Well, I'm not exactly sure what that is. And I think most non-pathological randomized algorithms would also work out. Okay, so just to support this conjecture, we looked at threshold functions, which are extremely simple, well-studied class, surprisingly interesting. So threshold functions are just functions that are 1 if and only if your point x is above some threshold. And these are defined over the real line, for example. BC dimension is 1, but the previous result would give a conditional mutual information of log n. But we're able to show that there exists an ERM for threshold functions with constant CMI, but this is in the realizable setting. So there's not like the agnostic setting where we allow, so we assume that the examples you're given are consistent with some threshold function. And the algorithm for this theorem is very simple. It's just output the largest threshold that gives you zero loss. And this of course satisfies the consistency property that we mentioned, so it's very natural. And the idea in the analysis is also that instead of just looking at the support size, we look at the actual distribution of the output, which is not uniform, so we're able to beat that log n, and it ends up having a geometric distribution. Yeah, that's sufficient to bound the CMI. It's just 2 bits. Okay, so wrapping up. So the things I've sort of shown you is that CMI provides a framework for reasoning about generalization. It implies generalization, and it is implied by several existing frameworks. We sort of show that we are able to give a unifying perspective, I guess, on some of these things like VC dimension and differential privacy. Provides a wide variety of generalization guarantee. It's not just a single generalization result at the end. I personally think that's some indication that we're doing something interesting here. So the obvious question for future work is what else can we fit into this framework or some extension of this framework? So a natural question is uniform stability, or stochastic, which is also a framework for studying generalization with a very beautiful and well-developed theory. And one example within that would be something like stochastic convex optimization. And I'm also keen to study relationships to other information-theoretic approaches. So one very well-known information-theoretic approach is the Pack-Bayes framework. And although it's sort of intuitively, there must be some connection, they don't really have like a formal statement. And of course, extending it to obtain higher probability bounds, I think that would be nice. And I'm also keen to have a better and more clear picture of how this relates to adaptive data analysis. We have some thoughts on this at the end of the paper, but that's something I still want to flesh out a bit more. I think the real question is, does this provide some new insights or some new results that we didn't really have previously? Thanks.
Awesome. Thank you, Thomas, for the excellent talk. Yeah, we have time for questions. Anyone has questions, feel free to just unmute and ask. We can ask questions as long. No one's kicking us out, so you can hang out as long as Thomas has patience for us.
I know my wife might come in and kick me out.
Hi, I have one quick question.
Okay.
You said that CMI framework has some potential to stochastic convex optimization. Can you elaborate on that a little bit?
I mean, I don't know. That's a question for future work. I'm keen to study what the relationship is. I mean, there are starting points. So, for example, there's work in differentially private stochastic convex optimization, and we could certainly immediately port some results over. But the question is, can we get stronger results than just the immediate translation?
Okay.
Other questions?
I have a bunch of questions, but I'll just ask one for now. What was the actual thing with the differential privacy? So you showed this like delta TV result. Is there some result?
So we haven't actually worked out the right parameters for that. I think it's going to be something like a half epsilon squared plus delta.
Yeah, as in like the half epsilon squared is like a multiplicative thing, and then the delta is additive, or what?
Yeah, so if you have epsilon delta differential privacy, I think you would get a half epsilon squared plus delta all times n CMI.
I see.
Which is kind of weird because typically we think of epsilon and delta as being quite incomparable. So the fact that you're just kind of looking at the sum of them is a little weird.
why do you get the epsilon squared multiplicative times n?
Because you're ultimately proving this via the chain rule for mutual information. So you're summing it over n guys, so everything gets multiplied by n.
I see.
So the generalization bound you'd get from that would be order of like epsilon plus square root of delta or something like that?
Something like that, yeah. Which I think is the right dependence, right? I mean, in terms of the direct analysis from differential privacy to generalization.
You only get epsilon plus delta, but maybe it doesn't matter that much. Yeah, I'm not sure. I'm unused to thinking of delta as being larger than epsilon, so I might have the wrong asymptotics anyway.
It's not really larger.
Well, so if it's large, if it's not larger, then you can ignore. It's just
right.
Just sort of the regime that I
yeah, I mean, it is a weird parameter regime. I'm not used to thinking of them being sort of comparable in some sense.
Right. But the mutual information bound for the CMI bound for epsilon delta dp, that's what you would get. It's sort of, if you have a product distribution over like an alphabet of two possibilities, then it's a mutual information. It's the mutual information bound you would get if the alphabet were just size 2. Is that correct?
Yeah. I mean, ultimately, you have to bound this Jensen-Shannon divergence in terms of your epsilon delta. Right, so I can go back to that slide. Where are we? Yeah, so ultimately you're bounding this thing here, so half P0 from P0 plus 1 over 2 plus P1 from P0 plus P1 over 2. And now your P0 and P1 are things that you're relating via whatever distributional stability notion you had, so epsilon delta. Right, so if you bound that quantity, then multiply that by n and you get a bound on the CMI.
All right, any other questions or like general questions? We can, afterwards I'll take us offline if you want to, go back and forth with Thomas a bit more. Going once, going twice. Okay, I guess that's about it for now. So again, I'll take us offline in a second. You can chat more with Thomas. I just want to remind everyone that the next talk is going to be 3 weeks from today, where Venkat Guruswamy is going to be speaking. Thanks a lot for joining us, everyone.
Yeah, great. Thanks for listening.